Engineering 305, example problem 2-6. A plastic bar with a circular cross-section of diameter 1.25 inches, 1.25 inches, will be used to support an axial load of 1,000 pounds, as shown in figure 220A. Determine the normal and shearing stresses on section AA. AA is given in the picture, just some arbitrary location, angle, and we're supposed to figure that out, how that goes. So I think I'll start out by, well, let's get rid of the problem statement and slide this up a little bit. If we were just doing this normally, and when I say normally, I mean if we were just looking at the stresses on this end face, that would just give us that this normal stress is equal to force over an area, and I'm going to put P because that's going to show up in the equation that we're going to use. In this case, we've got the oblique angle, and so we have to use the transformation equations from this section. And for this section, then those equations were right there at the bottom. That the normal stress, and I'm going to write it at the top here, the normal stress is equal to P over A times cosine squared of theta, where theta is that transformation angle. And there's the little figure that you see, I can't really highlight it very well, but it's measured from X to N counterclockwise in a kind of a right-handed rule sense, but from the X-axis to the N-axis, our axial stress has to be in the X-axis. So this figure is very important here. That's our X-axis. That's the direction that we're pulling. But this angle that they're giving us, theta of 33 degrees, is in the wrong direction. And so theta is not 33. Theta is equal to negative 33. And now we have enough information we can plug in. We go look at our figure. We have the load is 1,000 pounds. My area is the area of a circle, and so that's simply pi d squared over 4. And I should have probably put 1.25 inches there for d. And then cosine squared of theta. Well, here's I'm going to put, I won't put theta. In fact, I got to erase the whole thing because you can't erase half of something. You never get it quite right. Cosine squared of minus 33. And if you calculate all of that out, you get 573 psi. Now the other half of the problem would be calculating the shear stress. Let's get rid of these equations. Well, let's leave them there for a second. Sorry, that was a mistake. I am going to write down the equation. I'm going to write it probably right underneath. The shear in the n direction is equal to minus P over A times sine theta cosine theta. Now I could have used the sine 2 theta, but I think this is probably going to be just as easy or easier to punch in on the calculator. And when I do that, I get 372 psi. Now there's one thing, do I have a sense of that? Do I have... Yeah, it looks good. I mean, realistically, if what's the area of this is really how I would want to do my check. So d squared 1.25, that's going to get me, boy, what's 1.25 squared? About 1.5. And so 1.5 divided by times pi, that's going to give me about 4.5 divided by 4, a little more than 1. So that stress in this direction is going to be about 1,000 pounds, and then it's going to drop off as that angle changes. So I know that normal stress will be less than 1,000, less than. So yeah, these numbers are making sense, but at the same time, they should be in that area. Now, there's one other thing I can think about with this problem that might be interesting, and to show you that, I want to move this out of the way and pull up this figure again, because there's another way of looking at this face that I'm cutting on, and that would be what if I drew that as my normal? What if that were my normal? Now my angle, and I'm going with rainbows, now my angle is this. And theta is now equal to, it's in the positive direction. So that's, okay, so that's different. And it's going to be 57 degrees plus 90, or 147 degrees. That's going to give me, if you go back to our equations, which are on the screen again. Oh, still on the screen. I probably didn't uncover something for you, but you had the equation. You know what you needed. That's going to give us the same value for, when I'm looking at my equations, the cosine squared. That's probably like right there. Yeah, kind of hidden there. That's going to give me the same value for cosine squared. Even though it's negative, when I square it, it works out. And then sine theta and cosine, both of those have changed signs. So I'm still going to get a -1 in that second or fourth quadrant for that. So that's good too. Whichever angle I pick, or either the 147 or the 33 degrees, I'm going to get the same answer. Got a lot of lag in my pen. I don't know what the deal is. All right. Hope you're doing well. I'll say see you tomorrow, but tomorrow might be Saturday by the time you see this.